In this demonstration, what I'm going to do is take a classic problem that is actually it's from an algebra class. It has geometric principles and algebraic principles in it. It's the classic build a enclosed area with a given amount of fencing um, and find the maximum area basically. So I've constructed this diagram. Pretty simple construction. Um, what I'm going to do is explain what these figures are and then explore different things that you can tie into algebra as well as geometry. So what we have here, this bar on the top, this is the slider, and what this is going to do is it'll adjust the dimensions of the enclosed area, which is down here. As you can see, I have 10 centimeters of fencing. Obviously you would have to make the scale a little bit bigger if you're dealing with a true fence, but for modeling this will do just fine. So you can see here these two little segments here are the width of the fence, and these two bigger segments would be the two sides that make up the length of the fence. And what I'm going to do is take the width and plot it with the area, and it'll produce a point over in here. I will trace this point as I change this dimension to show the student what happens to the area as the dimensions change. And here's where you could talk about what it means when it touches 0, what it means when it gets up to the top there, what are those values that are up there, and then what happens there. So you can clearly see that it takes the shape of a parabola, which some students may know. I doubt they will, but in this case they can clearly see what it looks like. So that's one plot that you could have, is width or length versus area, produce the same graph. Another thing that can be shown and talked about is if you were just to plot length and width, and what kind of graph is formed there. And I believe, so I'll trace this point and I'll change the dimensions, and we'll see what kind of shape is formed here. And it appears to be a line. And at this point you could talk about why the line has a negative slope. Talk about an inverse relationship. As the width gets bigger, the length gets smaller, and why. We have a discussion about that. So there's a bunch of different things, what it means when it gets to 0, why can't it go past that point? Likewise on the y-axis, why it can't go past that point where everything went and everything disappeared. So that's a two-dimensional representation. Again, classic problem dealing with area, perimeter, and the thing I like about it is it ties in algebra as well. Now what I'm going to do is go to a similar type of question, but in this case we deal with 3 dimensions, and this is the classic problem where if you were given a piece of paper, what size cut would you have to make in the corner so that if you were to fold these 4 little flanges up and produce a prism, what would the largest volume be of that prism? Or what cut would give you the largest volume? So what I have up here is a slider that changes the length of that cut. And below it you can see the 3D representation of what the box would look like if that were the case. So I'm going to do similar with this one as I did with the previous one. I'm going to take, you could take any three of these values, length, width, and height, and plot them versus volume. I will do height, because actually height is what we want to see. If we're trying to figure out what the largest cut, or what dimension cut you would make here, that's one that you control. So that's one that I will use and plot that with volume. And you can see the point here, and we'll trace it and see what kind of shape is produced. And it appears like it's a parabola, but technically is not a quadratic equation, but it does have a maximum volume up on the top, which is the point that we're concerned about. Just see what happens here. Okay, so it appears that if you make a cut on this paper, on this model, about 1.3 centimeters, that will give you the maximum volume for that box, which is around 35. So now likewise with this, you can plot a bunch of different things. We'll try length and width. See what happens when you change the cut. You can see it has a positive slope. We can do length and height. See what happens there. You can see that has a negative slope. Or you could do width and height. You can see that, you know, they all have what appears to be the same slope, with one being the opposite, but they also have different intercepts. So you could talk about what those intercepts mean, what's the significance of the slope in this problem, what the significance is of the, you know, the maximum of that function that was plotted, what the zeros mean, etc. But there's a lot of things in here that you could talk about with your students and hopefully enhance their knowledge of not only volume, area, perimeter, and things like that, but tie in some algebraic concepts such as intercepts and maximum and minimums.